everyone. A very warm welcome to all the number experts. I am Tanisha Tyagi from S. Chan Publishing, and today, on the 31st of August, I welcome each one of you to this final session of the Math Summit 3rd edition under the CPT training by S. Chan Publishing. I hope you all are having fun and enjoying these sessions. Before we start our mega session, a quick reminder to all that at the end of this session, we will have a quiz for which I'm sure you all are eagerly waiting. We will share the quiz link in the chat box, so please stay tuned with us until the end. Today, we are exploring the fascinating world of cross-curricular integration, a topic that creatively bridges math with other subjects. And to guide us through this journey, we have the incredible Miss Jasprit Sethi, founder of Hatanoki Math with a Smile, with over 2 decades of experience as an educator, global trainer, and game creator, and a master's in mathematics education from Teachers College, Columbia University. Ms. Sethi has held key roles including Department Chair of Mathematics at the Bridgewater Lennox School and Advisory Board member for Teacher Education at Columbia University. She works extensively with children and learners, consults with schools, institutions, and government bodies, trains teachers and educators, and mentors parents and homeschooling families. Her work spans various domains and capacities, ranging from making teaching and learning experiences more meaningful to students and classroom management. And before we start our session, there are some housekeeping rules you need to follow. Participants will be muted throughout the entire session. Please ensure you have a pen and paper to note important information. The chat box will be enabled during the Q&A round and as requested by the speaker. To receive your e-certificates, please fill out the feedback form after the session. A quiz link will be shared at the end of today's session. The Google form link will be shared in the chat box for the quiz, and you will have to fill in all the mandatory details. The link will be active till 11:59 p.m. tomorrow, that is 1st September. Today's session will include guidance and tips from the speaker related to this topic. Now let's welcome our esteemed speaker, Ms. Jasprit Sethi. Over to you, ma'am.
Thank you, Tanisha, for the warm welcome. Thank you, S. Chan. This is an interactive session, and I would love everyone to take a moment and actually introduce themselves in the chat and tell me which part of the world you're from right now and how's the weather like over there. This is cross-curricular integration, and I think weather makes a big difference in how you are going to be placed today. So I would love for you to take a moment and share in the chat where you are from, which part of the world you're joining from, and how's the weather like over there? Awesome. Tanisha, I think we're seeing heavy rains. Yes, I think we're seeing a very diverse lineup of participants here today. Thank you so much, everyone. All right, let's dive right in as you can continue sharing more about where you're from and how's the weather like. I want to get into math and cross-curricular integration today. I'm very excited. I have in the past spoken about this at a very large scale, and coming back and doing this all over again with S. Chan is always a pleasure. So I'm going to start my screen share. I'll run you through the agenda real quick. So briefly in this 1 hour, I am going to be covering a few things. One is perspectives in math. And this always gets everyone talking, is math discovered or was math created? And then the other part is, do you want to or do you classify yourself as a math educator to be a math specialist or a generalist? And in
Ma'am,
that sense,
yeah, sorry to disturb. It's not in the slideshow mode.
I'm sorry, please say that again.
The PPT is not in the slideshow mode. Like we can see all the slides.
I just put it in slideshow. Please let me know if is it
Uh, no,
visible
ma'am.
now?
No, ma'am. I think you need to reshare it.
All right, sure. I'll stop share and start again. Thank you for letting me know that. How are things now?
Yeah, perfect, ma'am.
All
Perfect.
right, great. And the other thing is to take away from is I in that sense everyone is a math generalist. And then what objects and situations from real life can we use to inspire math talk? And how can we use concepts from history, social sciences, arts, languages, and science, of course, in math? So I'm going to start with a question and you can type in the chat. What do you observe as I show you this picture? What do you notice? What is this? All right, we got two of the same responses, three of the same responses. All right, now comes that difference. Thank you so much. Yes. Okay. As an animal, some of you may look at this as a rabbit, and some of you may look at this as a duck. I hope I'll take a moment for you to absorb both of them, because if you've only looked at it from one angle, you now want to see it from the other side as well. A duck or a rabbit. And this amazing illustration kind of is a segue into what I want to share as the first part of my agenda, which is that there is a perspective which is Platonic, that math truth and mathematical truths existed independent of human thought. And then as time went along, that math was basically just discovered and not created. For example, the Pythagorean theorem existed in some abstract sense before Pythagorean recognized it. And even before that, actually, if you go back to Vedic math in Bodhya and Sulvar Sutras, we already have evidences of knowing about the Pythagorean theorem without calling it the Pythagorean theorem. So has math always been there and it's just been discovered? And also this thing about universal consistency, that 2 plus 2 is 4 in all cultures, in all languages. And there is this universal truth to math. The other side of things is that math is a product of human thought and invention. So when you look at all of these symbols or these notations, those were not there. And over time, to be able to represent some sort of concept, we have made use of a way to show or represent that concept with a notation or a numeric value. For example, what's the number 3? There's nothing known as a number 3, except for I can count 3 objects and say that's 1, 2, 3. But what's the number 3? So there's that abstractness when it comes to math. I personally look at it from now in about 2 decades of being in math and pondering over math and teaching math. I think I'm somewhere in the middle here. That I'm sure that math existed and there's this abstract world that we just discovered, but definitely observing things in nature, it was human creation to be able to come up with a way to represent it using a model, using an equation, using a diagram, and all coming from inspiration. Everything pretty much came from nature. So in other words, when I look at it, I am looking at math as a very multidimensional subject. And if we go back even to history, we will see that most mathematicians were not pure mathematicians. They were also poets, they were also philosophers, they were also astronomers. So there's so much interconnect that was always there. It's only that, in the past few centuries, we have kind of segregated it as a different subject, when actually there's so much more if we study it holistically. The other part is, which I love to give as an example of specialist versus generalist, is, are you an elephant's right tusk doctor, or are you an elephant's doctor? So, and we need both. We definitely need both. But I, again, kind of lean towards the holistic part here. Of course, I will need a specialist if there is specific problem in the right task, and something needs to be done. But I like to put it in the form of some sort of a story here, that if there's a village and there's an elephant there who's showing signs of distress in its right tusk, you can call a specialist who can come and treat just that tusk. And then you'll realize that maybe that elephant's problem, or that distress, or a situation is still not getting resolved. And there's a systemic problem there, where the diet, the habitat, the interaction of that elephant with other elephants is also affecting the elephant. And there is where a generalist role comes in, because there you need a very holistic line of treatment. So again, are we somewhere in the middle? It's really important to understand that pure mathematics is a beautiful domain. And there's a lot of intrinsic beauty as well as logical structure that comes out of number theory, for example. But when I talk about the maths that we are exposing our children to in school, and then how we are expecting them to be able to transform that knowledge to real world, has to have some sort of connect. So you can bring in some pure math pattern or sequence, and I am going to indulge you in one shortly. But there has to be some sort of connect to be able to get the child who is in a nascent stage of understanding what their likes and dislikes are, and to somewhere make some sort of intersection point has to happen. So here is a sequence for all of you to play along with. What is the relationship from one term to another in this sequence? Take a moment and type in the chat. How do you observe going from one term to the next from left to right here, given this sequence? What kind of a sequence is it? So we have some of our participants telling us it's an arithmetic progression. Arithmetic progression would mean that I have the same constant term being added or subtracted here, which is not happening. It's not an AP. Is it a GP? Is it geometric progression? Am I dividing every time by the same value, or am I multiplying every time by a constant ratio? Not sure about that. Take a moment and see if that is happening. Actually, no, not arithmetic, not geometric. And if you say that the second number is half of the first number, is that happening every time? Is that going from the first term to the second term to the third term? Is that what I can say is one constant, either a common difference or a constant ratio? If you take a moment, there is so much more in here than what meets the eye. I've had students try to use some sort of operations to start telling me that, what, maybe I'm subtracting a 3, then I'm adding a 7, then maybe I'm, and then they see some pattern and they say, no, I'm not subtracting 3, maybe I'm dividing by 2, and then I'm adding a 7, and then I'm dividing by 2, and then I'm not adding a 7, but I'm adding an 11. So what's really going on there? Actually, all of you have right now, and I'm so happy that you're playing along, have indulged in an unsolvable problem in math. It's called the Collatz conjecture, which starts with any positive integer n. And if n is even, the rule is to divide by 2. And if it's odd, you're going to multiply by 3 and then add 1. So what I gave you is when I took my n to be 6. And I have to repeat the process. You'll see that at the very end of this, multiple repetitions may be required. And you're going to always reach 1. Always reach the number 1. Let me go back to the sequence. This was the sequence. And I started with 6 as my n. So because it was an even number, I divided by 2, I got a 3. But then because I got an odd number, I multiplied by 3, I tripled it, and then I added 1. So I am doing that repetitively until I'm seeing that I'm reaching 1. And you can start with any value to do this. For example, I'm starting with 11 and I am still repeating to reach 1. Now, this is a pure math problem, and someone would say, what's the relevance? Why do our kids need to know this? Here's the thing. Actually, it has a lot of relevance. One is the idea that complexity that is arising from simple rules. And also, this iterative process of applying the same rule repeatedly is leading to this complex sequence, which is actually relevant in chaos theory and dynamical systems. But it's also talking about the fact that how visually beautiful something can be, that how all paths are eventually converging to one, no matter what, no matter which number you've taken here. So there is a lot of beauty in the specialist side of math, but our section today is to focus on the cross-curricular integration and to be able to see some real-world examples. So I begin with something so nascent and so beautiful when it comes to population growth. And you can start with bacteria, you can start with anything. I have one, and every hour there is a double of that. So in the second hour, I have 2 of what I began with. And then in my third one, that's going to be my 4, as opposed to my fourth one, where I'm seeing 8 of them, where I'm seeing a double of what I began with. Now I can look at this problem as a pure math and just exponential growth situation. But I can link it to biology. I can link it to economics and statistics to address broad and complex issues. So my role today is going to be, as far as possible, to share ideas with you in how to integrate many other subjects with math, because and what are the connections there. So if I have a roller coaster and I think about what all math I can actually use in terms of a roller coaster, well, in the higher grades, and I'll share something with middle school as well, and even before that for primary. But in higher grades, I'm looking at my roller coaster as not just a roller coaster, but basically a lot of parabolas and some circles for the loops. And I can use and apply trigonometry to determine angles of inclines, declines, and the loops. I can use algebra to describe the path and the speed of the roller coaster and understand the force and the movement within the structure. I can use calculus and I can find the rate of change of speed and acceleration, ensuring that all these loops that my roller coaster is going through is giving me a very smooth transition and not a bumpy ride. And I can use physics to understand how to design and what's the design of that speed, the momentum, and how to ensure the safety of the roller coaster. So there's so much math and integration of math with subdivisions of math, as well as with science over here and design, to be able to make a very realistic roller coaster. For middle school level, if you want to go back a few steps, you want to start with just looking at these as pure lines. And those curves are made up of very small lines. And at each point, I can look at going uphill or downhill and calculate slope. What is slope or gradient? It's basically rise over run. What is rise and what is run here? It's the change in the height and the ratio of the change in the height to the change in the horizontal distance. So I need this information to be able to understand that what will be the change in elevation in each track here versus how much distance am I going to travel, to be able to know the gradient or the slope of each of these loops. The other thing is, again, coming back to primary, or pre-primary is to give them the experience of a very small roller coaster, as simple as a slide, and what that feels or looks like in terms of coming downhill. The other places where you want to integrate math, and there's so much math in design, in objects and situations, such as when you're going for any historic place, there is geometry, of course, that comes in terms of the architecture of the place. But there's also so much beauty in terms of the patterns, the shapes in the building design, um, and even in terms of fabrics or weaving. For example, if you're from India, um, we have so many fabrics that are using and so many intricate patterns on them, which make use of some beautiful geometric principles. So there's something known as ajrak, and there's ikat, and there's a sanganeri. And in all of these, if we look at how much distance from one object to another, and how to space out to know that I am not going to have some sort of a cut like this, which ends up happening inevitably depending on the meters or the yards of fabric that you're buying. How many can fit? How to even place that cloth to be able to have that kind of a design? There is a lot of math in there. Then in everyday objects, again, before I get into specific subjects and integration, would be, and this has troubled design experts for a long time, how many things can fit into a box, and what would be the best way to package. So these are basically, some of you can refer to these as paper rolls that are going into the receipt machines for transactions, or this could be toilet roll or kitchen towel, whatever you want to refer to this as. How many of these are fitting into this box to ensure that there is minimum wastage, and I can place maximum amount of these cylinders in this cube or cuboid. So there's so much in here in terms of everyday objects that you can bring in for very rich math talk. And then get, instead of those mundane textbook problems, to actually get students to do all calculations with something that you have really brought in from the environment, from your immediate environment. And if you can't bring it into your classrooms, you can always take a picture and project it to be able to get them to visualize how much math is being used. And, this could be a very, I could make this a simple word problem with about 4 or 5 sentences. It doesn't have the same beauty as it would be to just bring in and let them do the measurements, let them measure the length, width, and height, let them go ahead and get the radius and the height, and then use all the maths that is required to be able to know how many are going to fit inside. And there's so much more: cost of packaging, how thin should the material be, and there's where you can bring in more math. Here is one with here these are oranges, but you can think of these as even tennis balls. And what's the most optimal way to actually fit those into for packaging? What would be the best way to do that? And that has actually been a problem that a lot of mathematicians have tried to solve for a really long time. Today, we look at it and we're standing on the shoulders of giants. So we look at a lot of things today and we say, oh, this was so obvious. It's not actually. Look at how many iterations have been done to get back to understanding that actually the best way to be able to package is in a sausage shape. So those are different, trials and errors that have made us reach the point that we are today to be able to make conclusions that we do. Within one was the object and situation part. Now I want to get into the subjects that we have at our disposal, being in a beautiful school that is a large canvas to paint on. Our classroom may be a math classroom, but getting out of that classroom, there is so much more in there, and we can connect with our history teachers, our geography teachers, our global perspective teachers. And I will talk about art and music and design, as well as science, to be able to see how we can bring this all together. So with history, geography, global perspectives, I have to say that the history of human civilization begins with some sort of counting. So history of math gives you lessons in geography, archaeology, economics of the world. If I travel through different artifacts, and this is a 20,000-year-old Ishango bone found in Congo. I'm seeing actually a series of marks, and many scientists believe that these are tally marks, trying to keep track of some sort of counting that is happening in the immediate environment. Other physical objects like bones or stones have been used again to keep track of some sort of quantity. So we are seeing all this in history, in archaeology. Also, if we travel through how math has developed the math that we know today, the math that we use in a textbook, and how that has transformed, we have much to credit our initial early civilizations and how math has traveled for us to see the math we see today. For example, Mesopotamia, which is modern day Iraq, Syria, and Turkey, had different civilizations within it, like the Babylonians. So this is what you can see in terms of a modern day map. And we had the Assyrians, and we also had the Sumerians. And in all of this, there's so much math that has come through, which, for example, with the Sumerians, we credit them with the base 60 or the sexagesimal number system. And we use it today in terms of when we talk about 360 degrees in a circle, or there are 60 minutes in an hour. We have to give credit to how math has traveled, from being discovered, if it may, from one civilization to another. And it's not that parallelly another civilization was not discovering it or using it or realizing it, but in terms of timelines, here's one very small way to be able to look at it. Then Babylonians, where we are seeing some Pythagorean triplets actually on this Plimpton tablet. And thanks to Assyrians for understanding the volume of materials to be able to make a ziggurat like this, which is a temple. What were the volume of materials that were being used, needed? How did they even land up there to stack them up? What was the load that each terrace would bear? And how did they align it to be able to, with specific celestial bodies? Because most of these ziggurats had to be aligned in a way that it actually, either the sun was in the center or some other celestial body was in the center. How did they do that? So there is so much to credit the journey, and then bring in how Egyptians, and how we need to give enough credit to Egyptians for our base 10 decimal system. And we can see that in these hieroglyphics. We see some form of place value here, and very sophisticated, but really beautiful. And if you want to simplify it, look at it as almost trying to do a hundreds plus tens plus ones sort of a situation. And then, of course, India with zero and so many other elements that have come in from crediting the Indus Valley civilization. And our numerals today, which is, so it traveled, there were Roman numerals, and then but they were very sophisticated to be able, they were really good for record keeping, but very sophisticated to start doing any sort of calculations with them. So how that journey has traveled, and how we again have to give enough credit to how we have gone from what the numerals really looked like to what they look like today, and how the world over uses them. And then use of X in as a variable. So there is so much, I'm not going to read through the slides, but there's so much beauty in all of the history that and the geography that's there with math, to then transition into so many other subjects, such as art, nature, craft, design, music, sports. And then eventually, of course, the biggest, the marriage that we have with science. So art, with primary, one of the most underutilized tools is a grid paper. Grid paper is nothing but your box paper, and a lot of numeracy notebooks for many schools look like this. They are boxes. But we don't utilize these boxes enough. We only use these boxes to write numbers in them. So much drawing can happen here. What math concepts can I see in this little grid? Can we have some of you please type in the chat? What are some math concepts that I can relate to? Looking at it is just a drawing. What all am I trying to show here in this grid paper? All right, thank you for playing along. Perfect. Area, perimeter, numbers themselves, rectangles, symmetry, shapes, transformations, basic operations, fractions. Yes, thank you. Transformations, patterns, symbols, so many things. So I loosely, before anything, look at this as partners of 5. What are partners of 5? Numbers that add up to 5. 2 and 3, 1 and 4, and so many different ways to make a 5. This is 1 plus 2 plus 1. This is 5 in a row. This is 2 and 3. This is 4 and 1. This is also a 2 and 3, but shown differently. So orientation is something I can use from here. Partners of 5. I can use operations, giving away, taking away something, putting them in groups and arrays, doing multiplication division with it. I can look at this in terms of odd and even. What is an odd number? What is an even number really? If you get 1, I get 1, you get 1, I get 1, and we keep doing this, if I'm always left with 1, no matter what, and we've done that equal division, that is an odd number. So I can see this throughout because all of these are 5s. But if you're going to, from this, cut something and use it as a 4 or a 2, or combine something and look at it as 10 or 8, you'll see those evens, because if you get 1, I get 1, you get 1, I get 1, we're left with nothing after we've done an equal division. So that's odd and even. Fractions, I can look at this in terms of if this was a 10 by 10, or I give a simplistic version first to my students and get them to tell me what fraction of it is shaded, what fraction of it is not shaded. And then equivalent decimal, same thing can be converted to a decimal or percentage situation. Look at this in terms of an area problem. Look at this in terms of a perimeter problem. Take it out and make it into cubes and look at it in terms of a volume problem from going from 2D to 3D. Look at it in terms of your views. Top view looks like what? You know, if this was a structure, then if this is my top view, what could the whole structure look like? If this is my front view, if this is my side view, what does it look like? So there's so much that you can bring in with just pure art in primary. What am I doing here? I'm getting my students to try to just look at some cubes and look at a 10 by 10 and look at some individual cubes as well. And if I want to make this into a math lesson, we're just getting my kids to play around a little bit with their DNS blocks. These are DNS blocks. I can go ahead and then make it a math question by getting them to tell me how many are there and all. So different structures to be able to create that number, for example. This would be a simple primary problem, but you can definitely make it a middle school or a high school problem with calculation of each of the volumes for each of these, because as you can see, even visually right now, the weight looks different in terms of what these ones and these hundreds versus these thousands are in terms of weight. Another one, art, simple art, just a brick wall. And I transform that into a fractions problem. Then all I'm trying to do here is that I am doing half and then 1/3, and the same thing is being cut into 1/4, and the same thing is now being cut into 1/6. And why did I skip? Why did I not do a 5? Could there be a 5 there? What would that look like? And then I am now going into 1/8. And now finally, what have I done? I am going into 1/12. So how that same piece, that same could be chocolate, could be anything that you want to refer to, or piece of fabric or a ribbon, is being cut into different pieces. And they are all equivalent fractions, absolutely. So there's so much beauty in trying to bring in art into your, integrating all your math with art in the primary. How does it transition into the higher grades? I have seen artists using, for example, to draw this pencil, a cone and a cylinder. And to show depth or perspective in art using so many math principles. Furthermore, and this is usually just a single page somewhere in a textbook, and it should come out of the textbook to see this in live, is the Fibonacci sequence. To be able to tell students what a beautiful sequence that we have studied, which is coming from nature, but we're also using it in so many other places. So those of you who have seen this in lip service and nobody has ever really clarified it, I want to take a moment and talk about it. What happens with the Fibonacci sequences is that it's a pattern of numbers, and each one that's coming now left to right is going to be a sum of the two before it. So this one, for example, is a sum of the 0 and 1. And now this 2 is a sum of the 1 and 1. So how is this relevant? Actually, all the numbers, if I take them and I take the subsequent number and I divide it by the previous number, beyond my 0 and 1, I'm going to see something beautiful known as the golden ratio, which is actually consistent. That is one constant, but this is an approximation here. It is 1.615 or 1 and 615 thousandths. And it's actually evident in many natural patterns and also used in design because of its beauty and symmetry. So I see this in flowers. I see this in, I see these fractals in nature, in aloe vera. In paintings, we've had so many amazing artists use this principle. In design, and this is studied, and we have a beauty of just being able to look at a picture and scale it down to see this. But we have to appreciate where it was actually used, and in the architecture as well as the design of things. And in today's time, as relevant as a logo, which is using the golden ratio to be able to have the most precise symmetry, even in terms of, when we use a font and we have a heading and we have the subheading, or the text that comes under it, that also is distributed using the golden ratio. So this is a 20-point font versus a 12-point font. And again, that ratio that I take from that 20 to that 12 is the golden ratio approximately. The other thing is to be able to use math and design. Here is a cake artist who's using cake, not just bakes cakes, but decorates cakes. And that's an art in itself. So there's so much math involved in what are the ingredients that are going to be used here, what are going to be the cost of the ingredients. Let's go ahead and find out the proportions of the ingredients. Even for color mixing, what kind of colors will I need to mix to get these different shades of pink? What's going to be the weight of this cake, and about each tier, what's going to be the weight of each tier? How will I decide that? How will I bake that? Do I have containers for that? What's going to be the packaging or the delivery of it? Let me go ahead. Yes, absolutely. Mensuration right there. Can I go ahead and find the radii of the circles? These are cylinders really, but if I look at it from top view, these are circles. Can I find the radii of the circles and also these circles? And how thin or thick should they be? How many would I need? How many of these small circles do I need to actually cover this entire tier? And what's going to be the radii of the cylinders? What's going to be the price of the cake? How will I determine food color safety? Am I using, colors that are naturally safe? Am I mixing them in a way that it's edibly safe for the eaters? How is this different, or how do I save money, or how does this change the aesthetics if this is fondant or sugar really versus just a bread cake? Are my eaters going to be equally happy having a simple bread cake that is not as decorated? So there's so much that goes in math that is going into design as well. Here we have a pottery farm, and you're going on a field trip, and you can turn it into a math problem, and so many math problems. For early years and primary kids, it's about arrays and how these pots are arranged, and how they are kept in a way that it makes it easier to count, maybe at least on the stacks or the shelves here. But then how does it transform into a high school or the higher grades middle school math problem? Would be that what does and how does the height to the diameter ratio affect the stability of the cylindrical shaped pot when you're actually doing pottery? How much clay do you need to make a pot of a specific size? How do I determine that? How do I account for the wastage that I may have in terms of my design? And how do I make sure that my design stays symmetrical on the potter's wheel? There's so much that you can bring in. And how can we make sure that we have consistency, that the weight or the structure of one particular bowl is going to be similar to another bowl if you're being commissioned in a restaurant to supply these for a set? So that set should look alike, or should we have different sizes? And then there's going to be always some fight with customers how my cylindrical glass or dal or whatever I have poured that in, whatever's gone into pouring into that, earthen structure, how is that different from the other table? So how do I maintain symmetry? How do I maintain consistency? There's so much. The other thing is that we do not, and it's sad, but I will talk about solutions and fixes in terms of time and the constraints of time for a math teacher on how to even do this and how to get this done. But I want you to play along a little bit, even with nets. We sometimes only show our kids the usual nets of a cube or a cuboid, or maybe we may go up until to a triangular prism. A lot of the beautiful nets that they may see in nature, we kind of don't show them. So here is the dodecahedron, and that is having 12 pentagons, basically. Those faces are pentagons. And how does this relate to something that they can connect with? Is that if I also look at the 20 triangular phased icosahedron, which is actually something that they will see as some of the shapes of some viruses. Their shells are of this net, mimic this net, is when they play. If they are playing football or soccer, you are seeing actually a combination of the two. In what sense? If you have only 12 pentagons, where I showed you the net, but I have 0 hexagons, and hexagons, as you know, are made of 6 triangles, you get a dodecahedron. But if you have 12 pentagons and 20 hexagons, then you get this football. So a football or a soccer, that pattern is basically a truncated icosahedron. Awesome. Great. Then again, relating to life, bringing in real world objects to do some math with the kids. Here I have coconut oil, and there are different kind of cartons or different bottles for the same oil. Of course, one basic math is in terms of, if this was an art class, get them to design this. If they can make this with clay, or they can actually create this, and then why are we using plastic versus glass versus metal? What could be the ways in which we are going to be more sustainable and respect our environment? But also then go back to a lot of the economics of it. That why is it so that here I have a 200 ml bottle which is for 200 rupees, and I can then find out the cost for per ml. And this my 600 ml is for 219 versus 331 for 1 liter or 1000 ml. What's happening right here? Why do you think the cost is going down per ml? And that's a question that I have for all of you to ask here, and take a moment to actually respond in the chat. What is happening? Why is the cost going down? Why does it go down? And if as a math teacher, you cannot answer this, you want to bring in economics teachers on board because of economies of scale. and also something known as diminishing marginal utility. What is that? Basically, if I'm going to produce more, I am going to have my fixed costs spread over more units. I'll have a learning curve. That means that I will get more efficient with every manufacturing product that I'm going to keep manufacturing. The first time I made it, I may not be so good. And the more I make it and the more I get into the market, the more I learn. And I get better in terms of, where to procure my raw material from, how to get the cheapest, but the best quality in there. And also this fact that consumption, if you were really hungry and you are eating pizza right now, the first slice, you were really hungry and you really enjoyed the pizza. The moment it reaches the fourth or the fifth slice, you are now not that hungry. So, generally speaking, the more of a product you consume, the less additional satisfaction you're going to get from each extra unit. And that's where you can bring in your economics teachers and involve them in the lesson. Another very common one in finance that I usually see is why compound interest versus simple interest. And they're both taught as isolated topics. Simple interest, here's the formula. Compound interest, here's the formula. I want to take you through a very real world example. Here I have Dina, who is depositing 1,000 rupees in her savings account, and she's getting 2% annual interest. One is compounded and one is simple interest. How does that even look like? I'm not going to use any of the formulas. I'm just going to go with basic math here for you to play along with me and see how I can first show that, then transform this whole lesson into a formula class, and let them actually derive some of the formulas from the basic calculations. So basic calculation here is that I'm trying to do for the simple interest 2% on the 1,000 to know what's going to happen in year one, which is going to be 20 rupees. And then at the end of 3 years, consistently every year, I'm earning 20 rupees, and that's going to give me 60 rupees at the end of 3 years. I've not used PRT. I've not introduced any of those variables. For the other one, I'm doing 2% on 1,000, which is 20, which was also done in simple interest. But now the new amount that I have, my principal, is not 1,000 anymore. I have earned 1,020 with the interest included into that 1,000. And now when I do 2% on that, I see a 20 and 4 tenths. Where if it's in terms of money, then 20 and 40 paise or whatever currency denomination we're talking about. And then again, I have to include this 20 and 4 tenths into that 1,020. And then when I do 2% on that, I'm going to get this value. And then when I add up my year one, year two, year three, I'm going to see that I'm approximately getting 61 rupees and 21 paise, which I can now see as a comparison is, obviously I have a very small number to see a very small increment or difference here. But the more I will save or the more I will borrow, the more interest I have to either get or pay. So there is a lot here to talk about than to just then say that, here is simple interest, here's compound interest. Bring in finance into it. A lot of times for decision making, and a lot of times we as adults, grown-ups, are using these situations and we're using so much math, but we are sadly not involving our kids in any of these. For example, if I need to buy a laptop, if I have a high schooler or I have almost a seventh, eighth grader, I can definitely get them involved in telling me and researching the features and how are they useful to me. Because there's so much in terms of choice, where if you just go ahead and type in laptop for a particular size, but then I'm seeing all these terms. What does EMI mean? What would GST mean? And what do I need to know about customer service and repair? Do I have enough centers of, if I'm trying to buy a Mac, do I have enough customer support centers in my country or in my state to be able to then go to these places for repair if something happens? What do I still need to learn and ask from my computer teacher about so many of these features that I have no idea about? So there is so much that when we bring in informed decision making and tie it into a lesson, we will be seeing a lot more relevance from our children, and they'll thank us in years to come for the maths that we have introduced, which is not simple a word problem, but connecting it to their world or to their life. So here's another one. Firstly, to wrap this box, what do I need to know? If I need wrapping paper to wrap this box, or if I have to package this box, do I need to get volume? Do I need to find out surface area? What kind of maths do I need? So if I need surface area, what does that even look like? That looks like that I understand the faces of this cuboid, that I understand that here is the same as the other side. What I have here is what I have here. What I have on top is what I have at the bottom. And there is where you bring in the surface area formula to say that's twice the length width plus width height plus length height. Give them a real world situation and then go into the math is what I one takeaway that I would definitely share with you. Language teachers, we have so much English in maths, or even if we are not teaching it in English, we have to use the local language to be able to communicate or explain to a child in simple language what this question means sometimes. And it gets harder and harder. So here we have an English teacher who has used the about 400 some digits of pi and gotten a child to write a poem to be able to memorize the digits going by the number of letters in the word. And there's so much that you can bring in, especially as a science teacher as well. And science, there's, it opens the Pandora's box because there's so much math in science and so much science in math, and we do not have enough time to always collaborate. But I have actually come up with a simple table for elementary, middle, and high for you to take back to begin with on seeing how much you can in terms of EVS, environmental science or science, and in physics, chemistry, biology, bring in math. And I think one of the biggest things and most underlooked things in elementary is to introduce them really well to the different systems, the metric system, the customary system, to be able to do conversions really well. The other thing to keep in mind is to go into ratios and proportions really well, because there's so much that goes into chemistry with mixtures and concentrations that I have to understand ratio. And in high school, to be able to use sound waves, light waves, music, and principles of trigonometry and calculus. So really quickly, I'm not going to get you to try to solve this question, but I have some examples of this in action in classrooms where I have been, and how I have used a science class where we were trying to mix salt and water, and we were looking at different ratios. Talking about gold, or white gold in this case, being made from these different metals, and they are in a particular ratio, and then I want to know what would be the weight of this white gold ring that I'm trying to create. Trigonometry and the entire unit circle, or just our table, is just sometimes we just get kids to memorize the 0101 without realizing where it's actually coming from. So here I have a classroom where we were using sound waves and we were understanding music and trigonometry. So, and there's physics involved in terms of waves and wavelength and amplitude right out here. So here's a beautiful example of trying to show pitch versus beat. So if I have beats, for example, I say boom, boom, da, boom, that's my beat. But if I have my string instruments and I'm trying to go in some sort of a scale, and no matter which language you sing in or know something about music, if you go from a particular pitch, from a high pitch to a low pitch, how much of math is and physics is being used in terms of the waves that are being created here. So at this point, I want to bring you into almost a conclusion. There are limitations of our syllabus portion completion. lack of time. I think every teacher is going to relate to this. But there's also always this, I think, limitation of just teaching a skill, the algorithm, without connecting it to a concept. And that's where there's a lot of disconnect, especially in case study based questions in high school, in boards, where children are not able to connect to what they are reading and how it even applies to their world or their life. The other thing is to be able to understand that a lot of times we are looking at ourselves as specialists and not generalists. So, with all these limitations, how to fix and what could be some solutions to come to a stage where you can embed some of these into your classrooms? Well, one of the first things that I have tried to do as a math educator is to understand that everything ties back to number sense development. That a lot of times basic concepts are not clear. And then how can we build on those higher concepts when kids don't understand fractions and they don't understand divisibility rules, or they don't understand algebra? How to make it relatable? And I have developed a game for that called Yonju. And I have a lot of different exercises and challenges that I keep putting out there to keep it going in terms of the number sense element of it. The other thing is to have more dedicated time, definitely, to plan as a group rather than being an individual and planning as a sixth grade, seventh grade, fifth grade teacher. Please bring in all the fifth grade teachers if you can to plan together and see if you have thematic units where you can do some sort of cross-departmental planning. The other thing is to bring in a culture of problem solving into your schools and your classrooms. That there is some sort of a problem of the week which is very different from the textbook problem, which is something that they will not see in a textbook, which is very novel and something where they are going to use critical thinking, problem solving, or concepts from different strands within math. It could involve geometry as well as statistics, or it could be interdisciplinary to ensure that you are having time, if not in your classroom, at least the corridors are, almost reverberating of math and math talk, rich math talk. And the other thing is to be able to get me on board if needed as a consultant to your schools to show you how to do it in action, because sometimes as having the textbook as our canvas, we are not able to get out of that to see what all is possible within the time that we have. And I, one of my works as of today is to go into schools and going to design math weeks to demonstrate all of this in action. So over to you, Tanisha, and all the questions if we may have. I'm going to give it a wrap, and I want to thank our wonderful audience for playing along. These are some challenges, Yonju challenges. If you want to reach out, feel free to do so. And thank you so much, S. Chand, and thank you so much, participants, for being a wonderful audience. We'll take up
Participants, we can take up few questions. If you have any questions or queries, feel free to drop them in the chat box.
So we're seeing some great feedback. Thank you so much. I think they need to be staying tuned for the 5 p.m. quiz. Is that correct, Tanisha?
Yes,
That
yes,
follows
ma'am.
right after?
Yes, ma'am.
All right.
Okay.
Please show the last two slides
Yeah.
again. Sure, I will do that. So that's how you can reach out to me. And these were two Yonju challenges that are also out there that you can take back and maybe explore with your kids. And there are many, many, many more. Do we have any other questions?
Yeah, there's one.
As I said, Kuldeep, and who has a very relevant question, which I think a lot of people would have in terms of how to, embed all this. Well, one is reach out and ask, and I'm happy to share so that you can put some of these questions. But it'll be a disservice to your children to just see these questions on a test and you've not done it in a classroom ever before with them. So definitely, please, make it a culture in terms of problem solving as well as on the bulletin board to be able to have these sort of connections if you're not able to bring it directly into the classroom right away. Thank you so much, everyone. Thank you for your insights. To reach out to me, you can email me, and my email is right here. Thank you, everyone. Thank you so much, Eschan. Thank you. We've wrapped up this mathematical summit today, and I think now we are in for this amazing quiz and some amazing prizes. So all the best to everyone here. Thank you.
Okay. Thank you so much, ma'am, for captivating and enlightening us throughout the session. This virtual journey has been incredible, expanding our knowledge and deepening our appreciation for the beauty of mathematics. Your ability to connect with the audience, create an interactive atmosphere, and respond to questions with patience and clarity has been instrumental in making this a fruitful learning experience. I would also like to extend my gratitude to each participant who actively engaged in this year's Math Summit. Your eagerness to learn and ask questions has made these sessions vibrant and enriching. Now let's move on to the most awaited part of the session, the math quiz. I know you all are excitedly waiting for it. So participants, you can check the chat box. We have pasted the quiz link. Participants, as you can see, we have pasted the quiz link in the chat box. Please copy it. The link will be active till 11:59 p.m. tomorrow. If you want to revise the concepts of all the sessions, you can visit the website conferences at Ishan Publishing. We have shared the link as well. There you can watch all the sessions on YouTube. You can get all the YouTube links there and you can revise the concepts and then you can take up the quiz. Hmm. Participants, we have also sent the feedback form on your registered email IDs. To get the e-certificate, you have to fill the form and you have to submit the form. Then you will receive the e-certificate on your email. So we have shared the feedback form link with all of you. You can check your Gmails for that. Fill the form and submit it to get the e-certificate. Hmm. Participants, we have pasted the quiz link in the chat box. Please copy the link from there and paste it in another tab. Urvashi Singh, we have already pasted the quiz link in the chat box. Please copy it. The link will remain active till 11:59 p.m. tomorrow, that is 1st September. Shalini Bharat, you will get the link. Just wait for a few minutes. You will receive the email of feedback link. We have just mailed you guys, so it will take 2 to 3 minutes. So be patient. You'll get the feedback link in your inbox. Please copy the quiz link. We'll close the session in next 2 minutes. So I request all of you to copy the quiz link. The quiz will remain active till 11:59 p.m. tomorrow. That is 1st of September. And if you want to revise your concepts, we have pasted the website link also. There you can see the YouTube links of each and every session. Participants, please copy the quiz link. If you have copied, please, you can leave the meeting. If you want to revise your concepts before attempting the quiz, please visit our website. We have pasted the link as well. And there you can access all the sessions of this math webinar series. And our feedback form, you will receive the feedback form in your inbox. You will get the feedback form in your inbox. It will take 2 to 3 minutes as we have a number of registrations. So please be patient. You will receive the feedback form. So hope all of you have copied the quiz link. Now we are closing this session. Thank you so much for attending this Math Summit, third edition. Ganesh, you will get the feedback link in your email ID. Please check it. It will take up to 5 minutes. Please have some patience. Thank you. Thank you everyone for joining us today. Thank you. We are ending the session.